Albert Einstein's journey into the world of science and genius did not begin with a childhood full of brilliance that everyone immediately recognized. In fact, his earliest years tell a very different story, one that is often misunderstood yet deeply significant in shaping the thinker he became. Born on March 14, 1879, in the city of Ulm in the German Empire, Einstein came into a world that was undergoing tremendous change. The late 19th century was an age of invention, an age of electricity, railroads, and rapid scientific progress. Yet within his home, the atmosphere was warm, filled with the care of his parents, Hermann and Pauline, who were middle-class Jews. Hermann ran a small business in electrical engineering, while Pauline nurtured the young Albert's curiosity with patience and affection. The family moved often, eventually settling in Munich, where Einstein began his schooling. From the very beginning, Einstein did not fit into the mold of what was expected of children in school. His mind was not suited to the rigid methods of rote learning and memorization. Teachers often saw him as slow to respond, quiet, and even somewhat withdrawn. It is well documented that his speech developed later than other children, and this led to myths that he might have struggled intellectually as a child. In reality, his silence was not a lack of intelligence, but a sign of deep thought. His family noticed how carefully he observed the world around him, how he asked questions that went beyond the surface, and how his imagination seemed constantly at work. Even when he was only 5 years old, a moment occurred that would remain etched in his memory forever. His father showed him a compass. Watching the needle mysteriously point north, unaffected by the way he turned it, the young Albert was struck with wonder. How could something invisible exert such a force? That invisible presence, that unseen law of nature, lit the spark of curiosity that never left him. It was his first brush with the unseen forces of the universe, and it ignited a hunger to understand the mysteries hidden beneath everyday appearances. Despite this growing passion, Einstein's school life was a series of struggles. The German education system of the time was authoritarian and rigid. Students were expected to follow strict rules, obey without question, and repeat lessons from memory rather than think critically. Einstein resisted this approach instinctively. He found little joy in the repetitive drills and harsh discipline. Teachers considered him a dreamer, someone who was not cut out for academic success. Some even went so far as to suggest that he would never amount to much. But in truth, while he seemed disengaged in class, his mind was racing elsewhere. Instead of memorizing facts, he was thinking about light, about sound, about the invisible structures that governed nature. He read books outside the curriculum, explored ideas far beyond his grade level, and even taught himself mathematics and physics to satisfy his curiosity. At the age of 12, Einstein encountered a book that would transform his world, a geometry textbook. He later described this discovery as a kind of holy little geometry book, a treasure that opened his eyes to the logical beauty of mathematics. Unlike the rigid memorization of school lessons, geometry allowed him to see clear truths derived from reasoning. He delighted in the elegance of proofs, the certainty of mathematical relationships, and the sense that here was a language capable of describing the order of the universe. For Einstein, geometry was not just a subject but a revelation. He devoured the book, working through problems with enthusiasm, often surprising his family with his sudden bursts of joy when he solved a difficult theorem. This passion for mathematics would become the foundation of his later scientific breakthroughs. As he grew older, Einstein's independence of mind became both a strength and a challenge. His refusal to conform often put him at odds with teachers. Stories are told of one teacher who became so frustrated with his unwillingness to simply accept authority that he told young Einstein he would never succeed in life. Another described him as a disruptive influence, someone who undermined the seriousness of the classroom with his constant questioning. These criticisms did not discourage Einstein, but instead reinforced his belief that true learning came not from obedience, but from curiosity and exploration. His discontent with the traditional school system grew so strong that he eventually left school without completing his formal education in Munich. This was a bold step, as dropping out carried a heavy stigma, but Einstein was determined to find his own path. In the years that followed, Einstein's journey took unexpected turns. His family's financial difficulties forced them to move to Italy, and he joined them in Milan, leaving behind his formal schooling. While this seemed like a setback, it gave him the freedom to pursue knowledge in his own way. He continued to study mathematics and physics independently, driven not by grades or examinations, but by a genuine thirst for understanding. He read the works of great scientists such as Isaac Newton, James Clerk Maxwell, and Ernst Mach. Maxwell's theories of electromagnetism in particular fascinated him, as they hinted at deep connections between light and energy that would later play a central role in his theories. Einstein's path eventually led him to Switzerland, where he enrolled at the Swiss Federal Polytechnic in Zurich. Admission was not straightforward. At his first attempt, he failed the entrance exam, performing poorly in subjects outside his main interests. Yet his excellence in mathematics and physics was undeniable, and with perseverance, he was accepted the following year. In Zurich, Einstein found a more open and progressive environment that valued independent thought. Unlike the strict German schools, the Polytechnic allowed him to thrive, though he was still not the ideal student in the eyes of professors. He often skipped lectures, preferring to study on his own, and spent much of his time discussing ideas with friends or working through scientific problems independently. His brilliance was clear, but his unconventional style continued to challenge traditional academic expectations. What is striking about Einstein's early years is how his struggles became the very soil in which his genius grew. The rigid systems that labeled him a poor student only sharpened his determination to think for himself. The criticisms of teachers who doubted his potential pushed him to carve his own path. The compass that amazed him as a child, the geometry book that thrilled him at 12, the rejection from traditional education, all these moments wove together to create a mind unwilling to accept the world as it appeared on the surface. Instead, he sought to see deeper, to ask questions others would not dare, and to imagine realities that defied conventional wisdom. Einstein's early curiosity and educational challenges also highlight an important lesson about genius itself. True genius is not always recognized in classrooms or measured by exam results. It often emerges in those who dare to think differently, who refuse to be confined by rigid expectations. Einstein's story demonstrates that intellectual brilliance can sometimes be hidden beneath apparent disobedience, slow development, or rejection by authority. The very qualities that made him seem unusual as a child, his silence, his daydreaming, his constant questioning, were the seeds of the revolutionary thinker who would later transform physics. As he matured into a young man, Einstein never lost the sense of wonder that had begun with the compass in his father's hand. He carried with him a deep belief that the universe, no matter how mysterious, could be understood through reason and imagination. His curiosity was not a passing trait of childhood, but a lifelong force that guided every step of his career. Even before his most famous discoveries, the patterns of his mind were clear: a relentless questioning of assumptions, an insistence on clarity, and an ability to connect simple observations to profound truths. Thus, the story of Einstein's early curiosity and struggles in education is not one of failure but of transformation. It shows how obstacles can become opportunities, how doubt can fuel determination, and how a child once dismissed by teachers could grow into a thinker who reshaped humanity's understanding of space, time, and reality itself. Einstein's youth was marked not only by a rebellious spirit against the rigid school system, but also by a restless drive to understand nature in ways that others could not imagine. When his family relocated to Italy, Einstein wandered the streets of Milan and Pavia, spending countless hours in solitude, sketching ideas, and reading books that would shape his mind. He was fascinated by philosophy as much as by mathematics, Works by Immanuel Kant, Baruch Spinoza, and later David Hume gave him the foundation to think critically about the nature of reality, causality, and the limits of human knowledge. This blending of science and philosophy in his early years set him apart from the typical student who saw knowledge as separate compartments. For Einstein, everything was interconnected, and questions about the universe required both scientific rigor and philosophical depth. Yet, his life was not a straight line of uninterrupted progress. His refusal to conform to expectations brought difficulties that would frustrate him for years. At the Polytechnic in Zurich, where he finally found a place to develop his talents, Einstein's relationship with professors was often strained. His independent style was misunderstood as arrogance. He skipped lectures, argued about interpretations, and preferred to read scientific journals on his own. He was seen by some as undisciplined, even careless, but the truth was that Einstein's curiosity could not be contained by the ordinary curriculum. He studied Maxwell's electromagnetic theory with an intensity that few of his professors shared. He conducted thought experiments, imagining himself chasing a beam of light or watching how clocks might behave if one traveled at extreme speeds. These mental exercises, which seemed odd to others, became the seeds of the theories that would revolutionize physics. Despite his brilliance, Einstein's academic path did not flow smoothly into success. After graduating from the Polytechnic in 1900, he struggled to secure a teaching post or an academic position. His professors, unimpressed by his unconventional attitude, gave him poor recommendations. For 2 years, Einstein wandered in uncertainty, applying for jobs and facing rejection after rejection. To support himself, he took temporary teaching roles and gave private lessons. Eventually, through the help of a friend, he obtained a position at the Swiss Patent Office in Bern. On the surface, this seemed like a dead end for someone with his talents, a job far removed from cutting-edge science. Yet, in reality, it was another turning point born from struggle. At the patent office, Einstein examined inventions for their technical soundness, a task that demanded clarity, precision, and logical evaluation. This routine sharpened his analytical skills while leaving him evenings and weekends free to pursue his true passion, the mysteries of physics. During these years, Einstein's early experiences of educational challenges bore fruit in an unexpected way. He had learned to think independently because he was forced to. He had learned to trust his curiosity because teachers had dismissed him. And now, free from the pressures of academic expectations, he was able to dive into research with a sense of freedom. With a small group of friends he jokingly called the Olympia Academy, Einstein spent nights debating science and philosophy, reading the works of Henri Poincaré, Ernst Mach, and others who questioned the established foundations of knowledge. These discussions were not formal classes, they were raw, passionate explorations of the universe, carried out with the same wonder that had begun with the compass needle in his childhood. Einstein's so-called detours, the struggles in school, the conflict with teachers, the failure to secure an academic job, were not detours at all, but the very experiences that shaped his scientific identity. They gave him resilience, independence, and a profound respect for imagination. Unlike many of his contemporaries, who followed established paths, Einstein approached science as an outsider, unafraid to question the deepest assumptions. This is why in 1905, while working at the patent office, he published 4 papers that shook the world of physics to its core. These were the fruits of a mind that had been nurtured not by rigid education, but by curiosity, struggle, and the courage to think differently. But before the triumphs of 1905, the story of his early years reveals another dimension: his human vulnerability. As a young man, Einstein often felt isolated, misunderstood, and uncertain of his future. Letters to his family and friends reveal moments of self-doubt, of financial worry, of loneliness. Yet, through it all, he never abandoned the questions that haunted him. What is the nature of light? How does time behave at high speeds? Can the laws of physics be the same for all observers, no matter how they move? These were not the questions of a student aiming to pass exams, they were the questions of a thinker who wanted to grasp the essence of reality. The roots of these questions stretched back to his childhood curiosity, to that moment of wonder with the compass, to his fascination with geometry, to his rebellion against rote learning. His mother, Pauline, played a quiet but important role in shaping his perseverance. A cultured woman with a love for music, she encouraged Einstein to play the violin, a pursuit he carried throughout his life. Music became more than a hobby, it was a source of balance, a way to calm his restless mind. Playing Mozart or Bach on the violin allowed him to feel the harmony of patterns, the rhythm of beauty, and the order that he sought in the cosmos. This blending of artistic expression with scientific inquiry was not accidental. For Einstein, creativity was a universal force that applied equally to music, mathematics, and physics. The imaginative freedom he developed in childhood through music and philosophy supported the revolutionary leaps he would later make in science. It is worth noting that Einstein's challenges in education did not end with childhood. Even as a young adult, he remained skeptical of institutional authority. He disliked blind obedience and questioned traditional methods. This attitude, while sometimes creating friction with academic figures, kept his thinking fresh and unbounded. When others accepted Newtonian mechanics as an unshakable foundation, Einstein dared to imagine that space and time themselves might behave differently. When others studied light through experiments alone, he dared to conduct mental journeys faster than any laboratory could allow. These qualities were not cultivated in the classroom, but were forged in the struggles against it. His genius was not a product of conventional schooling, it was born from resistance to it. Looking back, Einstein himself reflected on these early struggles with a mixture of humor and insight. He once remarked that education is what remains after one has forgotten what one has learned in school. What he meant was that true education lies not in memorized facts but in the ability to think critically, to ask questions, and to remain curious. This philosophy was rooted in his own life. He never forgot the sting of being dismissed by teachers or underestimated by professors, and he never forgot the liberating joy of discovering truths on his own. It was this blend of struggle and wonder that defined his intellectual character. As the young Einstein moved from childhood to adulthood, the qualities that once made him appear slow, odd, or rebellious revealed their hidden value. His silence as a child had been the silence of observation. His resistance to rote learning had been the defense of imagination. His clashes with teachers had been the growing pains of a mind unwilling to be tamed. By the time he reached his 20s, these qualities had solidified into the intellectual courage that allowed him to challenge centuries of scientific belief. His story demonstrates how the seeds of genius are often misunderstood in their early stages, how brilliance may appear as defiance, and how a child once written off as a poor student could grow into the architect of modern physics. In the end, Einstein's early curiosity and educational challenges were not obstacles to be overcome, but essential parts of his journey. They taught him independence, sharpened his creativity, and nurtured his refusal to accept authority without reason. They shaped the man who, in the decades to come, would redefine space and time, illuminate the mysteries of energy and matter, and inspire generations to believe that imagination can change the world. When we celebrate Einstein as the genius who transformed our understanding of the universe, we must also remember the boy who marveled at a compass, the teenager who found joy in a geometry book, and the student who refused to conform. His struggles and curiosity were not separate from his genius, they were its very foundation. Thus, the first keynote of his life, his early curiosity and challenges in education, is more than a chapter in his biography. It is the blueprint of a genius shaped by wonder, defiance, and resilience. It reminds us that greatness is not always born in perfect classrooms or smooth paths, but often in the friction of struggle, in the freedom of imagination, and in the courage to think differently. Einstein's genius was not handed to him by education, It was forged against it, nourished by curiosity, and made immortal by his relentless pursuit of truth. The story of Einstein's revolutionary theory of relativity is one of the greatest intellectual transformations in human history. To understand how profoundly it reshaped our view of the universe, we must first recall the scientific landscape that existed before Einstein dared to question it. For more than 2 centuries, the physics of Isaac Newton had reigned supreme. Newton's laws of motion and gravitation provided a framework that explained the movement of planets, the fall of apples, and the mechanics of machines with astonishing accuracy. His ideas suggested that space was a fixed stage, time ticked forward uniformly for all observers, and objects moved according to predictable laws. Generations of scientists and engineers had built their work on this foundation, and for many, it seemed impossible that these principles could ever be challenged. Yet by the late 19th century, cracks began to appear. Experiments with electricity and magnetism, particularly those culminating in the equations of James Clerk Maxwell, revealed that light behaved as an electromagnetic wave. According to Maxwell's equations, light always traveled at the same speed, an idea that clashed with Newtonian expectations. If light was a wave, it seemed natural to assume that it must travel through some medium, much like sound travels through air. Scientists named this hypothetical medium the luminiferous ether. They imagined that the universe was filled with this invisible substance, a kind of cosmic stage through which light waves propagated. The existence of the ether was so widely accepted that few dared to doubt it. But in 1887, the Michelson-Morley experiment attempted to measure the Earth's motion through the ether and found nothing. Light appeared to travel at the same speed regardless of the Earth's movement, contradicting expectations. This puzzling result left scientists bewildered. It was into this landscape of confusion and unresolved questions that Einstein stepped with his special theory of relativity in 1905. Unlike others, he did not try to preserve the ether or patch up the contradictions with new assumptions. Instead, he asked a simple yet daring question: what if the speed of light is always constant for all observers, regardless of their motion? This idea seemed almost absurd at the time, but Einstein embraced it fully and followed its consequences with uncompromising logic. The results were astonishing. If the speed of light is constant, then space and time cannot be absolute. Instead, they must be flexible, relative to the motion of the observer. Time could flow at different rates for different people depending on their velocity. Lengths could contract when measured at high speeds. Events that seemed simultaneous for one observer might not be simultaneous for another. Space and time, once thought to be separate and rigid, were revealed to be interconnected, forming a single fabric known as space-time. This was not a minor adjustment to Newtonian physics. It was a complete reimagining of reality. The very notions of distance and duration, which seemed so self-evident in daily life, were now relative. Imagine 2 clocks ticking side by side, perfectly synchronized. If one clock were placed on a fast-moving train and carried away, observers at rest would find that the moving clock ticked more slowly than their own. This effect, known as time dilation, is not a trick of perception but a physical reality confirmed by countless experiments. Similarly, objects traveling close to the speed of light are physically shortened in the direction of motion, a phenomenon called length contraction. These consequences of relativity defy common sense, but they arise naturally from Einstein's postulates. In the years that followed, Einstein's theory of relativity spread through the scientific world, causing both excitement and resistance. At first, many physicists were skeptical. The idea that time and space could be relative, that the universe lacked an absolute frame of reference, seemed almost philosophical rather than physical. Yet experiment after experiment supported Einstein's conclusions. The theory explained the puzzling results of Michelson and Morley, resolved contradictions in Maxwell's equations, and provided a new framework for understanding motion at high speeds. Slowly, the scientific community began to recognize the brilliance of Einstein's insight. One of the most famous outcomes of special relativity was Einstein's equation N2 Derived from the principles of relativity, it revealed that energy and mass are interchangeable, two forms of the same underlying reality. A tiny amount of mass could be converted into a vast amount of energy, since it is multiplied by the square of the speed of light, a colossal number. This equation explained why stars could shine for billions of years, fueled by nuclear reactions that convert matter into energy. It also laid the foundation for technologies that would reshape the 20th century, from nuclear power to the atomic bomb. When Einstein first published this result, few understood its full implications. But as the decades passed, it became one of the most iconic equations in history, a symbol of both the promise and peril of modern science. The impact of relativity extended beyond physics into philosophy and culture. The idea that time is not universal, but relative to the observer challenged centuries of human thought. Philosophers debated its implications for the nature of reality, determinism, and the perception of simultaneity. Writers and artists drew inspiration from the notion of a flexible space, time, incorporating it into their explorations of human experience. Einstein himself became a symbol of the modern age, a thinker who had revealed the hidden structure of the universe and challenged humanity to rethink its most basic assumptions. Yet Einstein did not stop with special relativity. Over the next decade, he sought to extend his theory to include gravity, the force that Newton had described as the attraction between masses. Einstein was dissatisfied with Newton's picture of gravity as a force acting across empty space. Instead, he envisioned gravity as a manifestation of the curvature of space-time itself. Massive objects, like the sun, distort the fabric of space-time, creating a geometry that guides the motion of planets and light. This new theory, called general relativity, was published in 1915 and represented an even deeper revolution. It showed that the universe is dynamic, that space and time are not passive backgrounds but active participants in cosmic events. The predictions of general relativity were bold and testable. One of them was that light passing near a massive object like the sun should bend due to the curvature of space-time. In 1919, during a solar eclipse, astronomers led by Arthur Eddington confirmed this prediction, catapulting Einstein to global fame. Newspapers around the world hailed him as a genius who had overturned Newton and revealed the true nature of the universe. From that moment, Einstein became not only a scientific figure but a cultural icon, his image recognized worldwide. The impact of relativity on science was profound. It laid the foundation for modern cosmology, predicting phenomena such as black holes, the expansion of the universe, and gravitational waves, all later confirmed by observation. It influenced technology in ways unimaginable at the time. For instance, the Global Positioning System (GPS), used in everyday smartphones, must account for relativistic effects on time to function accurately. Without Einstein's theory, navigation satellites would drift out of sync, rendering the system useless. The once abstract equations of relativity became practical tools that shape modern life. But beyond its technical achievements, relativity transformed our philosophical relationship with reality. It revealed a universe far stranger and more interconnected than common sense suggests. Time was no longer a universal river flowing uniformly for all, but a personal dimension tied to motion and gravity. Space was no longer a stage on which events unfolded, but a fabric that could bend, stretch, and ripple. Humanity was forced to accept that its intuitive sense of reality, grounded in everyday experience, was only a limited perspective on a much deeper truth. Einstein himself often emphasized that the beauty of relativity lay not in its strangeness, but in its simplicity. He derived its principles from two clear postulates: the laws of physics are the same for all observers, and the speed of light is constant in all frames of reference. From these seeds grew an entire forest of new ideas. His genius was not merely in solving complex equations, but in daring to strip away assumptions and see the underlying simplicity of nature. This approach, rooted in his early curiosity and resistance to dogma, allowed him to uncover truths that others had overlooked. As relativity spread through the world, it changed not only science, but the way people thought about human potential. If the universe itself could be so radically different from what common sense suggested, then perhaps other assumptions in society could be questioned too. Einstein became a symbol of intellectual freedom, of the power of imagination to transform reality. His theory of relativity was more than a scientific achievement, it was a cultural milestone, a turning point in humanity's quest to understand its place in the cosmos. The impact of relativity continues to echo today. Astronomers use it to map galaxies, physicists rely on it to probe the quantum world, and engineers depend on it to build technologies. Each time we look at an image of a black hole, detect the faint ripples of gravitational waves, or navigate with GPS, we are living in the world that relativity made possible. The theory that once seemed abstract and strange has become a foundation of modern life. At its heart, relativity is a story of courage. The courage to question, the courage to imagine, and the courage to trust the results of reasoning even when they defy intuition. Einstein's willingness to abandon centuries of certainty and embrace a vision of space and time as relative forever changed our understanding of the universe. It stands as one of the greatest triumphs of human thought, born not of complex machinery or vast laboratories, but of a single mind daring to see the world differently. The acceptance of Einstein's theory of relativity did not happen overnight, nor was it without resistance. Many scientists of his time were deeply rooted in the Newtonian worldview, and for them, relativity was almost heretical. It challenged not only the mathematical structures of physics, but the very philosophy of certainty that had guided science for centuries. Newton had given humanity a universe of absolute order, predictable and stable. Einstein replaced it with a universe where time and space were flexible, where simultaneity was relative, and where the fabric of reality itself could bend under the weight of matter and energy. This was not just a new theory, it was a new vision of existence. Some physicists dismissed it as too abstract, others as too radical. But as experimental evidence accumulated, resistance gave way to reluctant acceptance, and then to admiration. Relativity was not simply a mathematical curiosity. It was a window into the true nature of the cosmos. The 1919 eclipse expedition, which demonstrated the bending of starlight by the sun's gravity, was more than just a scientific experiment. It was a public revelation. When the results were announced, newspapers across the world printed headlines declaring that Newton had been dethroned. Overnight, Einstein became a celebrity, a rare occurrence for a scientist. He was portrayed as a prophet of modern times, a man whose mind could see truths invisible to others. While Einstein himself remained modest, often reminding people that he stood on the shoulders of those before him, the public imagination elevated him into a symbol of genius itself. His wild hair, thoughtful gaze, and gentle humor became iconic. In Einstein, people saw the triumph of human intellect, the idea that one individual with courage and imagination could transform the understanding of the entire universe. The cultural impact of relativity was immense. Philosophers debated whether Einstein had destroyed the notion of objective reality. Artists experimented with new forms of perspective, inspired by the relativity of space and time. Writers incorporated the idea of multiple viewpoints and shifting realities into their works, paralleling Einstein's challenge to absolute frames of reference. Even ordinary people, though they might not understand the mathematics, sensed that something profound had changed. The world felt different, less certain, more fluid. The comforting stability of Newton's universe had given way to a universe filled with mystery and wonder. Relativity became not only a scientific revolution, but a cultural one, reshaping the way humanity thought about itself and its place in the cosmos. For Einstein, however, relativity was not a matter of fame or cultural influence but of scientific truth. He continued to refine his ideas, exploring the deeper implications of general relativity. The theory predicted remarkable phenomena, time running slower near massive objects, light losing energy as it climbs out of gravitational fields, the possibility of black holes where space-time curves so intensely that not even light can escape, and the dynamic expansion of the universe itself. Each of these predictions, once considered speculative, has since been confirmed by observation. Astronomers have watched time slow down near massive stars, observed light bending and redshifting as predicted, and even photographed the shadow of a black hole, a stunning confirmation of Einstein's vision. The discovery that the universe is expanding, first hinted at by observations in the 1920s, eventually led to the modern Big Bang theory, which rests firmly on the foundation of general relativity. Einstein himself was sometimes surprised by the far-reaching consequences of his work. He initially resisted the idea of an expanding universe, preferring to believe in a static cosmos. To preserve this view, he introduced what he later called his greatest blunder, the cosmological constant, a mathematical term to counteract expansion. Ironically, this concept has returned in modern physics as an explanation for dark energy, the mysterious force driving the accelerated expansion of the universe. It is a reminder that even the greatest scientific minds are shaped by the assumptions of their time, and that the full implications of a theory may take generations to unfold. The practical impact of relativity has also been profound. In the early 20th century, critics dismissed it as abstract and impractical. Today, it underpins technologies that billions of people rely on daily. The Global Positioning System is the most famous example. GPS satellites orbit the Earth at high speeds and experience weaker gravity than we do on the surface. Both special relativity and general relativity affect the ticking of their atomic clocks. Without corrections from Einstein's equations, GPS systems would accumulate errors of several kilometers each day. Every time someone uses a smartphone to navigate, they are unknowingly applying relativity. This is one of the most striking examples of how a theory born from pure thought experiments, from the imagination of a young patent clerk wondering about light beams, became a practical necessity for modern civilization. Relativity also paved the way for countless scientific discoveries. The search for gravitational waves, ripples in space-time predicted by Einstein in 1916, became a century-long quest. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected such waves for the first time, caused by the collision of two black holes. This detection confirmed one of Einstein's boldest predictions and opened a new era of astronomy. Instead of relying only on light, humanity could now listen to the universe through the vibrations of space, time itself. Each detection since then has revealed violent cosmic events, merging black holes, colliding neutron stars, unfolding just as Einstein's equations foretold. It was as though the universe was whispering its secrets in a new language, a language Einstein had taught us to hear. The reach of relativity extends even into the smallest scales of physics. Although Einstein himself struggled with the emerging field of quantum mechanics, his work on relativity influenced debates about the fundamental nature of reality. The tension between relativity, which describes the universe at large scales, and quantum mechanics, which governs the microscopic world, remains one of the deepest puzzles in modern science. Physicists seek a unified theory that can reconcile these two pillars, a quest often called the search for quantum gravity. In this sense, Einstein's legacy is not complete. It continues to guide the direction of science, challenging new generations to push further. Einstein often remarked that his theories were motivated not by ambition, but by a profound sense of wonder. He once said that the most incomprehensible thing about the universe is that it is comprehensible. To him, relativity was not merely a scientific achievement, but an expression of the deep harmony of nature. He spoke of the joy of uncovering the order hidden beneath appearances, comparing it to the experience of listening to great music. For Einstein, the equations of relativity were not dry symbols but melodies of the cosmos, resonating with beauty and meaning. This sense of wonder, more than anything, explains the enduring power of relativity. It was not just a set of rules, It was a vision of reality that touched both mind and spirit. The broader impact of relativity can also be seen in the way it changed humanity's perspective on itself. By showing that time and space are not absolute, that our experience of reality depends on our motion and position in the cosmos, relativity humbled human assumptions. It reminded us that our everyday perceptions are limited, that the universe is deeper and stranger than it appears. This humility, combined with the awe inspired by the vastness of space-time, has influenced not only science but also philosophy, religion, and art. Relativity became part of the human story, a milestone in our journey from ignorance to understanding. Yet Einstein himself never sought to impose his vision as final. He was always searching, always questioning, never fully satisfied. Even after relativity had been confirmed, he continued to pursue deeper unification, seeking a theory that would combine gravity with electromagnetism. Though he did not succeed, his persistence inspired generations of physicists to dream of unifying all forces. His willingness to embrace bold ideas while acknowledging their limits remains a model for scientific inquiry. As we look back today, more than a century after Einstein first published his theories, relativity stands as one of the crowning achievements of human thought. It has been tested in laboratories, confirmed by astronomical observations, and embedded in technology. Its predictions, once radical, are now accepted facts. And yet it retains the power to inspire wonder, to remind us that the universe is not a simple machine but a living fabric of time and space, full of mystery and beauty. The story of relativity is, in the end, not only about physics but about the human spirit. It shows what can happen when one person dares to ask questions that others ignore, when imagination is given free rein, and when reason is followed courageously to its conclusion. Einstein transformed not only the equations of science, but the way humanity thinks about reality. His theory of relativity is a monument to curiosity, creativity, and the limitless potential of the human mind. It is a reminder that the universe is vast, strange, and awe-inspiring, and that with courage and imagination, we can begin to understand it. When Albert Einstein first introduced the equation E = mc², the world could not have imagined how much those 5 symbols would alter the course of history. At first glance, it looked simple, almost deceptively so. Yet within its elegant form lay a revelation about the universe that would redefine the relationship between matter and energy, reshape modern science, and eventually influence the destiny of nations. The equation declared that mass and energy, once thought to be separate entities, were in fact 2 sides of the same coin. A tiny amount of matter could be converted into an immense amount of energy, and energy itself could give birth to matter. It was a radical vision, one that seemed almost philosophical when first proposed, but would later become one of the most consequential scientific insights ever discovered. To understand the significance of E = mc², one must recall the scientific context in which it emerged. In the early 1900s, physics was in a period of both triumph and uncertainty. Newtonian mechanics had successfully explained the motion of planets and falling apples, while Maxwell's equations had unified electricity and magnetism. Yet questions lingered. What was the true nature of energy? Why did the speed of light appear to be a constant, defying the rules of relative motion? Einstein's special theory of relativity, published in 1905, offered answers, and nestled within those answers was the seed of his most famous equation. E = mc² was not initially presented as a dramatic proclamation, but as a logical consequence of relativity, a quiet note at the end of a paper. Still, this seemingly modest idea carried implications that would reach far beyond the academic journals where it was first written. The equation tells us that energy equals mass multiplied by the speed of light squared. Because the speed of light is such an enormous number, about 300,000 kilometers per second, its square is almost unimaginably large. This means that even a tiny bit of mass, when fully converted, can release staggering amounts of energy. At first, this concept seemed almost like a mathematical curiosity. The everyday world did not show such transformations. A stone sitting on the ground did not spontaneously release bursts of energy, but Einstein suggested that this equivalence was not just theoretical, it was real, waiting to be revealed in the right circumstances. As science advanced, those circumstances would be discovered, and the power hidden in matter would be unlocked. The earliest confirmations of Einstein's equation came not from laboratories, but from the stars. Physicists soon realized that atoms explained how the sun and other stars shine. For centuries, the source of solar energy had puzzled humanity. Some suggested chemical burning, others gravitational contraction, but both explanations failed to account for the sun's billions of years of brilliance. Einstein's equation provided the missing piece. Within the sun's core, hydrogen nuclei fuse to form helium, and in the process a small portion of mass is converted into energy, released as light and heat. That light travels across space to warm the Earth, sustain life, and drive the cycles of climate and biology. In this sense, every sunrise is a living demonstration of atoms. Without it, our star would be dark, and life as we know it would not exist. The fact that the formula underpins the very energy of the cosmos shows its profound scope, connecting human life to the physics of the stars. As nuclear science developed in the 20th century, the practical implications of atoms became clearer. Researchers discovered that atomic nuclei contained immense binding energies. Under certain reactions, fusion in stars, or fission in heavy elements like uranium, mass could indeed be converted into energy, just as Einstein predicted. In controlled amounts, this offered new possibilities for energy production. In uncontrolled amounts, it held terrifying destructive power. The equation, which Einstein himself had derived from pure thought, became the scientific foundation for both the promise of nuclear power and the horror of nuclear weapons. Few scientific ideas have had such a dual legacy, at once a beacon of hope and a symbol of fear. The Second World War accelerated this transformation of theory into reality. Scientists working on the Manhattan Project applied the principle of mass, energy equivalence to design the first atomic bombs. By splitting heavy nuclei in chain reactions, they unleashed the energy hidden in small amounts of matter. The devastation of Hiroshima and Nagasaki in 1945 revealed to the world what atoms meant in practice. Entire cities could be destroyed by the conversion of just a few kilograms of matter. For many, this moment changed the perception of science forever. Knowledge was no longer only a path to understanding nature, it was also a force that could shape geopolitics, alter the course of wars, and threaten humanity itself. Though Einstein was not directly involved in the bomb's creation, his equation was forever linked to it, and he carried a sense of moral burden for the rest of his life. Yet to reduce atoms only to weapons would be to miss its broader meaning. The equation symbolizes the unity of nature, the idea that matter and energy are not separate kingdoms, but manifestations of the same essence. This insight opened doors in physics, inspiring new ways of thinking about particles, fields, and the fabric of reality. It provided the conceptual foundation for particle accelerators, machines that probe the fundamental constituents of matter by smashing particles together at high energies. Every discovery of new particles, every exploration of the quantum world at large colliders, is an ongoing demonstration of Einstein's principle. When energy in the form of motion or light is converted into new particles of matter, we see atoms in action, reminding us that the building blocks of existence are interchangeable in ways our ancestors could hardly have imagined. The equation also carries philosophical significance. It challenges the distinction between substance and activity, between what something is and what it can do. In ancient thought, matter was passive, a kind of inert stuff waiting to be moved by forces. Energy was something separate, an action or movement imposed on matter. Einstein's formula dissolves that boundary. Matter is itself a form of energy. Energy is, in a sense, frozen matter. The universe is not built from separate categories, but from a unified reality expressed in different forms. This holistic view resonates with both scientific inquiry and human imagination, offering a vision of the cosmos as a single interconnected fabric. Culturally, Ita Mensita became perhaps the most famous scientific formula in history. It appears on T-shirts, posters, and in countless references in books, films, and conversations. Its simplicity makes it accessible even to those who do not understand its depth. People may not know the details of relativity or nuclear physics, but they recognize those three letters and that squared symbol as a sign of genius and of scientific modernity. In this way, the equation transcended science to become part of popular culture, a shorthand for intellectual brilliance and the mysteries of the universe. Its iconic status reflects both its power and the fascination it inspires. Einstein himself was aware of the equation's importance, though he remained humble about its fame. He often joked that while people celebrated Ita Mensita's, very few truly grasped what it meant. For him, the formula was less about fame and more about beauty. He valued the simplicity of the relationship, the way a profound truth could be expressed in so compact a form. To Einstein, the best scientific ideas were not only correct but also elegant, resonating with an aesthetic harmony. Ita Mensita, in its brevity and power, embodied that ideal. It was science distilled to its essence, clarity born of deep thought. The scientific impact of the equation continues to grow even today. Modern cosmology, which studies the origins and evolution of the universe, relies on mass, energy equivalence to explain processes from the Big Bang to the present. The early universe was a seething sea of energy that crystallized into particles of matter as it expanded and cooled, a cosmic dance choreographed by Ita Mensita. Later, stars and galaxies formed, powered by nuclear fusion that again converted matter into radiant energy. Even in the far future, as stars die and black holes evaporate, the interplay of matter and energy will continue, guided by the principle Einstein revealed. His equation is not only about the past or the present, but about the fate of the cosmos itself. On a human scale, the dual promise and peril of Ita Mensita remain with us. Nuclear power plants harness controlled fission reactions to generate electricity, offering immense energy with relatively little fuel. At the same time, concerns about safety, waste, and weapons remind us of the dangers. Efforts to harness nuclear fusion, the process that powers the sun, aim to provide a cleaner, virtually limitless source of energy. If achieved, it would be a triumph of Einstein's equation, turning humanity's understanding of mass, energy equivalence into a sustainable foundation for civilization. Thus, the future of energy, and perhaps the survival of humanity, is tied to the principle of Ita Mensita. What makes the story of Ita Mensita so compelling is that it bridges the worlds of thought and action, of abstract theory and tangible reality. Einstein did not set out to build bombs or power plants. He sought to understand the nature of space, time, and motion. Yet from his search for truth emerged a principle that reshaped technology, politics, and daily life. It is a reminder that ideas have consequences, often far beyond what their creators intend. In this way, the equation reflects the dual nature of science itself, a quest for knowledge and a tool that can transform the world. In reflecting on the meaning of Ita Mensita, one sees not only the brilliance of Einstein, but also the collective journey of humanity. The equation connects the smallest particles to the largest stars, the laboratory to the battlefield, the realm of pure thought to the fate of nations. It embodies both the creative and destructive capacities of human intelligence. Above all, it illustrates the extraordinary power of ideas, how a simple equation born in the mind of one man can ripple across time and space, changing everything from our understanding of the universe to the way we live on Earth. The deeper one looks into the meaning of Ita Mensita, the more it seems like a bridge between the ordinary and the extraordinary. On one level, it tells us that matter and energy are interchangeable, that a stone, a tree, or even a human being contains hidden energy beyond imagination. On another level, it demonstrates the remarkable power of thought, that a mind seeking only to understand the laws of motion could stumble upon a principle with the capacity to transform the planet. It is difficult to think of any other scientific expression that has carried such weight in both imagination and reality. For Einstein, it was simply an unavoidable result of his equations. For humanity, it became a symbol of both wonder and responsibility. The social consequences of the equation grew most sharply in the 20th century. After Hiroshima and Nagasaki, the world saw the image of mushroom clouds rising above destroyed cities, and for many people, those images became inseparable from Einstein's formula. In popular imagination, Atom Masida was no longer just a law of physics but a shorthand for the atomic age. Politicians invoked it, artists depicted it, and citizens feared it. The Cold War, with its nuclear arms race, gave the equation a new political meaning. Nations invested enormous resources into building arsenals that could obliterate the Earth many times over, all grounded in the principle that a small amount of matter, split or fused, could release terrifying amounts of energy. The equation had moved from blackboards to missile silos, from thought experiments to global strategy. This was not the destiny Einstein had envisioned, and he often spoke out against the militarization of science. He signed letters, petitions, and public statements warning about nuclear proliferation, insisting that humanity must learn to use its newfound power wisely. Still, he could not control how others chose to apply his insights, and he carried the sorrow of that truth with him. Yet even in this dark chapter, Atom Masida also inspired visions of progress. Scientists and engineers sought ways to use nuclear reactions for peaceful purposes, to provide electricity, to power ships, to advance medicine. Nuclear energy plants, though controversial, became part of the modern world. Radiation, guided by the understanding of mass-energy equivalence, was harnessed to treat cancer, to sterilize medical instruments, and to trace biological processes. In these contexts, Einstein's equation was not a threat but a healer, showing again the dual nature of knowledge. The same principle that could destroy a city could also save a life. The responsibility lay not with the formula, but with those who wielded it. In the realm of science itself, atomic CDIs became the key to exploring the structure of matter. Particle physics, the branch of science that studies the fundamental building blocks of reality, is essentially an exploration of mass-energy transformations. At large accelerators, such as the ones at CERN, particles are smashed together at high energies, and the resulting collisions convert kinetic energy into new particles of matter. These experiments reveal the hidden symmetries of nature, the rules by which the universe operates at its smallest scales. Each discovery of a new particle, from the quarks to the Higgs boson, is another demonstration of Einstein's principle. Energy becomes matter, matter reveals its inner energy. Without Atom CDI, modern particle physics would be impossible, and our understanding of the universe's fundamental architecture would be far poorer. Cosmology, too, is deeply indebted to Einstein's equation. The Big Bang theory rests on the interplay of mass and energy at the dawn of time. In the earliest moments of the universe, pure energy condensed into particles, creating matter as we know it. Later, matter and antimatter annihilated each other, releasing bursts of energy, leaving behind the slight excess of matter that makes up the galaxies and planets. Even the faint cosmic microwave background radiation, the afterglow of creation, is a relic of these transformations. Atom Masida is therefore not only a principle of physics, but a principle of existence, a rule that explains how the universe itself came into being and continues to evolve. When scientists look through telescopes at the most distant galaxies, they are not only seeing light from ancient stars, but also witnessing the ongoing dance of mass and energy, described by Einstein more than a century ago. The equation has also reshaped our philosophical understanding of reality. It challenges the idea that matter is permanent and immutable. Instead, matter is dynamic, able to dissolve into energy and reappear in other forms. Nothing is truly static, everything is part of a grand exchange, a cosmic economy where mass and energy are currency. This perspective resonates with ancient philosophies that saw reality as fluid and interconnected. In a strange way, Einstein's physics converged with certain timeless intuitions about unity and change, bridging science and philosophy. It gave modern humanity a new language to express an old truth that everything is connected, and that the visible and invisible are not separate but expressions of the same essence. In education, the equation became a gateway for inspiring generations. Teachers often introduce students to atomic as a way to illustrate the beauty and power of physics. Even if the mathematical details are complex, the idea that a single formula can explain the sun's light, nuclear power, and the origins of the universe is captivating. It shows students that science is not just about numbers, but about ideas that touch the deepest mysteries of life. For many young minds, encountering atomic is the moment they realize that physics is more than equations on a page. It is a window into the workings of the cosmos. The cultural legacy of the equation also continues to grow. It appears in art, literature, and music, often as a symbol of modernity or intellectual daring. Filmmakers use it as shorthand for scientific brilliance, novelists as a metaphor for transformation. Even those who cannot explain the equation can feel its resonance, the way it stands for the triumph of human thought. In a world where science is sometimes mistrusted or feared, atomic remains a reminder of the wonder that knowledge can inspire. It is perhaps the only equation that has crossed into the realm of myth, joining the ranks of symbols that define eras and civilizations. Einstein himself remained wary of the mythologizing of his work. He often emphasized that science was a collective effort, that no equation belonged to one man alone. Yet he could not deny that atomic had changed not only physics but the world's perception of physics. Before Einstein, science was often seen as distant, a pursuit for specialists. After atomic science was part of everyday conversations, part of political debates, part of culture. People who had never read a physics paper could still discuss Einstein's formula, even if imperfectly. It was as though the veil between the scientific community and the public had thinned, and knowledge itself had become more democratic. Today, as humanity faces global challenges, the meaning of atomic is still unfolding. The dream of harnessing fusion energy, clean and abundant, is one of the most important projects of our time. If realized, it would provide a solution to climate change and energy scarcity, offering power without pollution. This dream is nothing less than an attempt to replicate on Earth the process that powers the sun, a process explained by Einstein's equation. At the same time, the risk of nuclear conflict reminds us of the darker side of mass energy conversion. The future of civilization may depend on how wisely we manage this double-edged gift. The equation is therefore not only a law of physics, but a test of humanity's wisdom, a challenge to match scientific insight with moral responsibility. What is striking about atomic is its enduring relevance. Unlike many scientific results that fade into the past, replaced by newer theories, this equation remains central. It is embedded in the standard model of particle physics, in cosmology, in astrophysics, in technology. It has been tested and confirmed countless times, yet it continues to inspire awe. Its simplicity makes it memorable. Its consequences make it profound. It is both a scientific tool and a cultural icon, a rare combination that ensures its place in history. In reflecting on this legacy, one cannot help but admire the mind that first wrote those symbols. Einstein was not working with powerful computers, nor with billion-dollar laboratories. He was working with thought, with imagination, with questions. He wondered what it would mean to ride alongside a beam of light, what it meant for time and space to be relative. Out of those questions came not only relativity, but also the revelation that matter and energy are interchangeable. It is a reminder that the most powerful instruments of discovery are not machines but minds, and that the greatest revolutions often begin with a single person daring to think differently. Ultimately, the meaning of atomic goes beyond physics, beyond bombs, beyond power plants or space telescopes. It is a story about the human capacity to see deeper into reality, to uncover truths that change how we live and how we think. It is about the light of the sun, the birth of the stars, the potential of our future, and the responsibility of our choices. It is a symbol of our highest achievements and our greatest risks. In those 5 characters lies a reflection of humanity itself: creative, curious, powerful, and vulnerable. The story of Itam and Sevi will continue as long as humanity exists, for it is not just a scientific equation but a key to understanding existence. Every sunrise, every nuclear reactor, every particle experiment, every reflection on the origin of the cosmos, all echo the truth that Einstein revealed. In the simplicity of those symbols lies the complexity of the universe, and in the discovery of that truth lies the greatness of the human spirit. Albert Einstein is remembered not only as a scientist who transformed the way humanity understands the universe, but also as a moral voice who spoke out about peace, justice, and the responsibilities of knowledge. At a time when the world was being shaken by wars, totalitarian regimes, and the dawn of nuclear weapons, Einstein chose to use his voice not only in the halls of science, but also in the public square. He believed that the role of a scientist did not end with discovery, but extended to the ways in which that discovery was used by society. For him, knowledge was inseparable from responsibility, and science had to be guided by conscience if it was to serve humanity rather than destroy it. Einstein had lived through some of the most turbulent decades of modern history. Born in Germany in 1879, he saw Europe collapse into the First World War when he was still a young man, and he witnessed the rise of fascism and Nazism in the years that followed. As a Jew, he was forced to leave his homeland and seek refuge in the United States, becoming one of the most famous émigrés of his generation. These experiences deeply shaped his views. He saw firsthand how nationalism, militarism, and hatred could tear societies apart, and he became convinced that only cooperation, compassion, and peace could safeguard humanity's future. He often remarked that the splitting of the atom had changed everything except human ways of thinking, and that without a moral awakening, science could lead to catastrophe. The most dramatic example of Einstein's moral struggle came with the atomic bomb. Though he had nothing to do with the Manhattan Project and did not work on weapons research, his 1939 letter to President Franklin Roosevelt, co-signed with physicist Les Szilard, warned that Nazi Germany might attempt to build a bomb based on uranium fission. This letter helped trigger the U.S. effort to develop nuclear weapons, something Einstein later regretted. After the war, he became one of the loudest voices calling for international control of atomic energy and the abolition of nuclear arms. He warned that humanity now faced a choice between survival and annihilation, between learning to live in peace or risking extinction. To him, the equation eta miceti was not only a triumph of science but also a burden, a reminder that the power of nature could either illuminate the world or reduce it to ashes. Einstein's voice carried great authority because it was not limited to politics but rooted in universal values. He spoke about the importance of human rights, freedom, and dignity. He denounced racism in America, calling it a disease of the nation, and he stood with figures like W.E.B. Du Bois and Paul Robeson in the struggle for civil rights. He advocated for Jewish refugees and supported the creation of institutions that would protect minorities and promote tolerance. For Einstein, peace was not just the absence of war, but the presence of justice, and justice required courage, compassion, and solidarity. His moral vision extended beyond national boundaries, and he often described himself as a citizen of the world rather than of any single country. He also placed his faith in international cooperation. Einstein believed that nationalism was one of the greatest threats to peace, and he argued that only a world government or a supranational authority could prevent future wars in the nuclear age. Though some critics dismissed his ideas as utopian, Einstein insisted that humanity could not afford to cling to old rivalries in a world where a single bomb could destroy a city. He joined organizations promoting disarmament and world unity, using his fame to draw attention to causes that might otherwise have been ignored. His speeches and writings carried the same clarity and conviction that marked his science. though now the equations were replaced by appeals to conscience and reason. Beyond politics, Einstein's commitment to peace was rooted in his personal philosophy of life. He described himself as a pacifist, though not in the absolute sense, for he admitted that some struggles, such as the fight against Nazism, might require force. But in principle, he believed that violence could never create lasting peace, that only dialogue and understanding could. He often spoke of the need for humility, reminding people that human beings are small in the vast universe, and that clinging to pride or hatred was both foolish and dangerous. His love of music and his sense of wonder at nature reflected this humility. He saw beauty and harmony as antidotes to the destructiveness of human arrogance. Einstein's advocacy for peace was not always welcomed. In the tense years of the Cold War, some accused him of being naïve, others of being politically suspect. His outspoken views made him a target of suspicion in the United States, especially during the McCarthy era, when intellectuals and activists were often smeared as radicals or subversives. Yet Einstein did not waver. He knew that silence would be easier, but he believed that truth demanded courage. Just as he had challenged the scientific orthodoxy of Newton, he now challenged the political orthodoxy of militarism. In both cases, he acted not for personal gain, but from a conviction that humanity must never stop questioning the assumptions that lead to injustice or destruction. In the final years of his life, Einstein reflected often on the meaning of peace. He urged younger generations to think beyond the divisions of their time, to embrace curiosity, kindness, and the pursuit of wisdom. He believed that education should not only train the mind, but also cultivate the heart, instilling values of empathy and responsibility. He saw science as a tool not only for power but for enlightenment, a way to lift humanity beyond ignorance and fear. To him, the greatest danger was not knowledge itself, but the failure to use knowledge wisely. If humanity could unite its intellectual achievements with moral maturity, he believed, the future could be one of progress and harmony. Today, Einstein's words about peace and human values still resonate. In a world still threatened by nuclear weapons, conflicts, and divisions, his voice calls us back to reason, compassion, and humility. He showed that a scientist could also be a moral leader, that genius is not only measured by equations, but also by the courage to speak for what is right. His legacy is therefore not only in relativity or etam ideals, but also in the timeless reminder that knowledge without conscience is dangerous, and that true greatness lies in using wisdom to serve humanity. Albert Einstein's life and work stand as one of the clearest examples in history of how progress is made, not by blind obedience to tradition, but by the courage to question authority. In the world of science, tradition carries great weight, and the figures who came before command immense respect. By the late 19th century, Isaac Newton's laws of motion and gravitation had stood for more than 200 years as the unchallenged foundation of physics. They explained the motions of planets, the fall of apples, the behavior of machines, and the very rhythm of the universe with extraordinary accuracy. For generations, students were taught to accept Newton's mechanics as absolute truth, and the idea of challenging them seemed unthinkable. Yet Einstein, with his quiet but relentless spirit of inquiry, refused to accept limits where logic and curiosity led him to doubt. Einstein had a temperament that naturally resisted authority. From his youth, he distrusted rigid systems, whether in school, politics, or science. As a student, he often clashed with teachers who demanded rote learning rather than creative thinking. He once remarked that the tyranny of rules and blind obedience suffocated true learning. This rebellious spirit carried into his scientific life. When others told him that Newton's vision of space and time was complete, Einstein dared to ask questions. He wondered what it would be like to ride alongside a beam of light, a thought experiment no textbook encouraged, yet one that opened a path to relativity. By pursuing questions others ignored or feared, Einstein showed that authority was not always a guide but sometimes a barrier to discovery. In the early 1900s, physics seemed stable, as if most of its great problems had been solved. Many scientists believed that the task of the future was only to refine and extend Newton's laws. But Einstein sensed cracks in the old structure. The puzzling results of experiments, such as the Michelson-Morley experiment, hinted that Newtonian physics could not fully explain the behavior of light and motion. Instead of dismissing these anomalies, Einstein embraced them. He trusted the evidence of reason and mathematics over the authority of tradition. In 1905, with his paper on special relativity, he shattered centuries of certainty by showing that time and space are not fixed absolutes, but relative to the motion of the observer. This was more than a scientific claim. It was a philosophical challenge to the very mindset that had placed Newton on a pedestal of untouchable authority. Einstein's work did not stop there. He challenged the very nature of light with his explanation of the photoelectric effect, suggesting that light could behave as discrete quanta rather than continuous waves. At first, this idea seemed radical and even absurd to many physicists who clung to classical theories. Yet Einstein persisted, showing again that progress often comes not from preserving tradition, but from daring to rethink it. This questioning attitude earned him resistance from established scientists. Some dismissed his theories as speculative or impractical. But Einstein did not fear opposition. He believed that science was not a matter of authority, but of evidence, logic, and imagination. In his view, one honest question was worth more than 1,000 acts of conformity. This willingness to challenge tradition extended to Einstein's interactions with his contemporaries. Even after relativity was widely accepted, he continued to question the emerging consensus in quantum mechanics. While most physicists embraced the uncertainty principle and the idea that nature was governed by probabilities, Einstein resisted. His famous statement, "God does not play dice with the universe," captured his refusal to accept randomness as a final explanation. Though history has shown that quantum mechanics has immense predictive power, Einstein's challenge kept the debate alive, reminding scientists that consensus should never silence inquiry. His disagreements with figures like Niels Bohr were not acts of stubbornness, but examples of his belief that questioning authority, even the authority of the new mainstream, was essential for truth. Einstein's challenges were not made recklessly. He did not reject tradition for the sake of rebellion. Rather, he respected the work of Newton, Maxwell, and others deeply, but believed that their theories were stepping stones rather than final answers. His genius lay in combining humility with courage, knowing that even the greatest minds of the past were limited by their time. He often said that imagination was more important than knowledge, for imagination allowed one to see beyond the boundaries imposed by authority. This outlook not only led to relativity, but also inspired generations of scientists to think creatively, to test assumptions, and to resist the comfort of easy answers. The broader significance of Einstein's defiance lies in how it reshaped the culture of science. Before him, many scientists felt constrained by the weight of tradition, hesitant to propose ideas that might seem too radical. After Einstein, the landscape changed. He showed that even the most sacred theories could be overturned by reason and evidence. His success gave courage to others to explore bold ideas, from the expansion of the universe to the weirdness of quantum entanglement. In this sense, Einstein did not only transform physics, he transformed the very spirit of scientific inquiry. He proved that progress is born from questioning, not from obedience. Beyond science, Einstein's challenge to authority carried a moral dimension. He distrusted political and social authorities that demanded blind loyalty, whether they were empires, dictatorships, or institutions. His resistance to militarism, nationalism, and racism reflected the same spirit that led him to resist intellectual conformity. Just as he refused to accept Newton's absolutes without questioning, he refused to accept the injustices of his age as natural or unchangeable. For Einstein, true freedom, whether of thought or of society, meant refusing to let authority silence the search for truth. Einstein's story reminds us that every breakthrough comes with the courage to ask, what if? What if space and time are not absolute? What if light is both wave and particle? What if authority is wrong? These questions, simple yet profound, shaped the course of modern science. They reveal a deeper lesson that reverence for the past must never become a prison for the future. Tradition can guide, but it should never dictate. Authority can inspire, but it should never silence. The world Einstein gave us, a world where space and time bend, where energy and matter are one, where even reality itself is open to question, is a testament to what can happen when one mind refuses to bow to the weight of convention. Thus, Einstein's legacy as a challenger of authority is as important as his equations. His genius was not only in discovering relativity, but in embodying a spirit of fearless inquiry. He showed humanity that no truth is too sacred to be examined, no tradition too old to be questioned, and no authority too powerful to be doubted. In doing so, he ensured that science would remain alive, dynamic, and free, a pursuit not of dogma but of endless discovery. Albert Einstein was more than a scientist. He was a cultural phenomenon whose influence spilled far beyond the boundaries of physics. When most people hear his name, they do not immediately think of the intricacies of relativity or the equations of quantum theory, but rather of an image: the wild hair, the thoughtful eyes, the gentle smile, sometimes the playful tongue sticking out. Einstein became a symbol of genius itself, a representation of intellectual creativity and human curiosity. His presence shaped how society imagined what it meant to be a thinker, and his ideas reverberated across philosophy, art, literature, and even politics, leaving a mark that endures far outside the walls of science. One reason Einstein's influence reached so deeply into culture was that his discoveries changed humanity's conception of reality in a way that was both unsettling and inspiring. For centuries, the universe had been seen as a stable, clockwork machine governed by predictable laws of Newton, but Einstein revealed a cosmos where time bends, space curves, and reality is far stranger than everyday experience suggests. This new vision fascinated not only scientists but also writers, artists, and philosophers who saw in it a metaphor for the uncertainty and complexity of modern life. The idea that time was not absolute but relative echoed in literature exploring the fluidity of memory and consciousness. The concept that space itself could be warped by matter resonated with artists experimenting with perspective and form. In this way, Einstein's physics became part of the cultural imagination, inspiring creativity far beyond the laboratory. Einstein himself was deeply aware of the philosophical implications of his work. He often reflected on the nature of reality, the role of human perception, and the limits of knowledge. His writings touched on questions that had occupied thinkers for centuries. What is time? Does the universe have order or chaos at its core? Is human freedom compatible with the laws of nature? His insistence that the universe was governed by laws rather than randomness influenced debates about determinism and free will, while his rejection of a purely probabilistic view of quantum mechanics stirred philosophical controversies that are still discussed today. For philosophers, Einstein was not just a physicist, but a fellow traveler who opened new pathways of thought. His theories became reference points in discussions of metaphysics, epistemology, and the philosophy of science, reshaping the intellectual landscape of the 20th century. At the same time, Einstein's personality and public presence made him a cultural icon. Unlike many scientists who preferred to remain in the background, Einstein's fame spread across the globe, making him one of the most recognizable figures of his era. Newspapers reported on his lectures as if they were grand events, and ordinary people who could not understand relativity still revered him as the embodiment of wisdom. He was humble, witty, and approachable, qualities that contrasted with the stereotype of the distant or arrogant intellectual. This human touch endeared him to millions, and his image became a shorthand for brilliance itself. Even today, when cartoons or advertisements need to symbolize intelligence, they often invoke Einstein's likeness or name. Einstein's influence also extended into politics and ethics. He was a thinker who used his authority not only to speak about science but also to comment on society's direction. His critiques of nationalism, militarism, and racism found their way into public debates and inspired activists who saw in him a voice of reason and compassion. He championed causes from civil rights in America to the call for world government, and while some dismissed his views as idealistic, many admired the moral clarity with which he spoke. His presence lent credibility to movements for peace and justice, showing how a figure from the realm of science could shape cultural values. In this sense, Einstein was not only a physicist but a public intellectual whose words carried weight across the world. The arts, too, reflected Einstein's influence. Writers like Virginia Woolf, James Joyce, and Thomas Mann grappled with ideas of time and consciousness that paralleled the relativistic worldview. Painters experimented with perspectives that broke with classical representation, echoing the ways in which Einstein had broken with the classical understanding of space. Even in music, composers sought structures that reflected the dissonance and fluidity of a relativistic age. Though Einstein himself was devoted to classical music, particularly Mozart and Bach, his scientific revolution resonated with the avant-garde movements that sought to capture the fractured, yet interconnected spirit of the 20th century. Einstein's role in popular culture also illustrates how science can become part of collective myth. His name entered everyday language, used as a synonym for genius. Films, plays, and novels often portrayed him as a sage, sometimes mystical, sometimes humorous, but always larger than life. He became a bridge between the world of complex theories and the imagination of ordinary people. In a time of rapid technological change and global conflict, Einstein symbolized the hope that intellect could illuminate humanity's path. Even his quirks, his rumpled clothing, his violin playing, his refusal to conform to social expectations, became part of his legend, reinforcing the idea of genius as something untamed and authentic. Philosophically, Einstein's work also forced a rethinking of human knowledge itself. By showing that even concepts as fundamental as time and space were not fixed but relative, he challenged the assumption that science provides eternal truths. Instead, he revealed that scientific theories are human constructions that evolve as our understanding deepens. This humility about knowledge influenced not only scientists, but also philosophers and educators, who saw in Einstein's example a model of intellectual openness. His life demonstrated that certainty is an illusion, and that true wisdom lies in continuous questioning. Moreover, Einstein's story inspired countless young people to pursue science. His fame made physics glamorous in a way it had never been before. Students who might otherwise have chosen different paths were drawn to study the mysteries of the universe, motivated by the example of the man who had unlocked its secrets. His impact on education was enormous, as his theories became central to curricula around the world, and his persona encouraged the idea that science was not only a profession, but a calling to expand the frontiers of knowledge. In the decades since his death, Einstein's influence has only grown. His face appears on posters, T-shirts, and coffee mugs. His quotes are shared as pearls of wisdom across generations. His theories continue to shape both scientific research and cultural thought. Few figures in history have managed to cross so seamlessly from the technical to the universal, from the pages of academic journals to the shared symbols of humanity. Einstein achieved this not by seeking fame but by embodying a life of curiosity, honesty, and imagination. In the end, Einstein's influence on culture and philosophy shows that science cannot be separated from the broader currents of human life. The equations of relativity were not just lines of mathematics, but windows into a new way of seeing reality, a way that poets, artists, and thinkers could adapt to their own visions. His life was not just the story of a scientist, but of a human being whose wisdom, humor, and courage touched millions. By bridging the worlds of science and culture, Einstein became a figure who belongs not only to physics but to all of humanity, a symbol of what the human mind can achieve when it dares to question, imagine, and dream. Albert Einstein passed away in 1955, yet his presence still lingers in the fabric of human thought, in the technologies that shape daily life, and in the very language we use to speak of genius. His name has become a symbol, his theories have become foundations, and his vision continues to guide humanity into the unknown. To speak of Einstein's legacy is to speak not only of physics, but of the enduring power of ideas, the responsibility of knowledge, and the courage to question. More than half a century after his death, Einstein remains both a towering figure in science and a cultural icon whose relevance has not faded with time. At the heart of his legacy lies relativity, a theory that redefined our understanding of space, time, gravity, and the universe itself. The general theory of relativity, once an abstract set of equations, is today an essential tool for modern technology. Satellites that guide navigation systems must account for the relativistic effects of time dilation to provide accuracy, making Einstein's insights part of the ordinary routines of millions around the world. Astronomers use relativity to probe the mysteries of black holes, gravitational waves, and the expansion of the cosmos, discoveries that confirm time and again the depth of his vision. Each new confirmation, whether through the detection of waves rippling through space, time, or the image of a black hole's shadow, extends his legacy, showing that his theories are not relics but living guides for exploration. Beyond the practical applications, Einstein's legacy is philosophical and cultural. He taught humanity that reality is not always as it appears, that common sense can mislead, and that truth requires imagination as much as calculation. In an age still defined by rapid change, these lessons resonate. His life is a reminder that one person with curiosity and persistence can alter the destiny of knowledge. He embodied the principle that discovery belongs not to institutions or authorities alone, but to the power of the human mind when it dares to ask bold questions. This message continues to inspire scientists, thinkers, and dreamers who seek to push beyond the boundaries of the known. Einstein's legacy also endures in his moral voice. He did not confine his life to equations. He used his authority to speak about peace, justice, and responsibility. In a world that still struggles with war, inequality, and prejudice, his calls for compassion and unity remain relevant. He reminded humanity that knowledge without conscience is dangerous, that the splitting of the atom demands the mending of human hearts. His vision of a world beyond nationalism, beyond hatred, still challenges society to strive for greater wisdom. To remember Einstein is not only to recall a scientist, but to hear again a voice urging peace in a turbulent age. His influence on education is another thread of his lasting impact. Einstein valued creativity over rote learning, curiosity over conformity. He encouraged students to ask questions rather than memorize answers, to cultivate imagination as a path to discovery. Today, educators continue to invoke his philosophy as a model for nurturing minds that think critically and creatively. The countless young scientists who entered physics inspired by Einstein's example testify to his role not merely as a discoverer, but as a mentor across generations. His story continues to draw children toward science, making him a beacon for the future as much as for the past. In the realm of culture, his legacy is even broader. Einstein has become a symbol of genius itself, recognized across languages and nations. His face appears in art, advertising, and popular media not simply as an image of a physicist, but as a representation of human potential. His quotes circulate widely, offering wisdom on life, imagination, and humility. While this cultural fame sometimes oversimplifies his work, it also keeps his presence alive in the collective imagination. Einstein the scientist became Einstein the myth, and that myth continues to inspire ordinary people to believe in the power of ideas. The future of Einstein's legacy also lies in the questions he left unanswered. His discomfort with aspects of quantum mechanics, his search for a unified theory of nature, remain unfinished journeys. Modern physics continues to wrestle with these challenges, from string theory to quantum gravity. each attempt in some way echoing Einstein's quest to unify the laws of the universe. In laboratories and observatories, his influence guides the search for deeper truths. Even when physicists disagree with him, they do so in dialogue with his thought, proving that his presence still shapes the path forward. Einstein's vision of science as a universal endeavor is also part of his lasting mark. He saw knowledge as belonging to humanity, not to nations or races. In an age when science faces challenges of inequality, misinformation, and mistrust, his example of openness and honesty serves as a model. He lived modestly despite his fame, never seeking wealth or power, but dedicating his mind to the service of truth. This ethical dimension of his legacy encourages future generations to see science not only as a tool of progress, but as a responsibility to humanity. Even in everyday language, Einstein's name is woven into how people think of brilliance. To call someone an Einstein is to recognize intelligence, yet also perhaps to recall the image of a thinker unafraid of being different. His eccentricities, his humor, his simplicity made him relatable. He showed that genius need not be distant or cold, that the most profound ideas can emerge from a person who enjoys playing the violin, taking long walks, or laughing at himself. In this way, Einstein's legacy humanizes genius, reminding people that greatness is not perfection but passion, persistence, and imagination. In reflecting on his enduring impact, one must see Einstein not as a figure frozen in history, but as a presence that continues to evolve with humanity. Each generation discovers him anew, whether through school lessons on relativity, images of black holes confirming his equations, or the moral force of his words about peace. His life is a bridge between past and future, showing how one individual can embody the spirit of inquiry that drives human progress. Einstein's enduring legacy is therefore multi-layered. It is scientific, in the theories that still guide exploration of the universe. It is cultural in the image of genius that inspires curiosity and imagination. It is moral, in the call for responsibility and compassion in the use of knowledge. It is philosophical, in the questions about reality, time, and existence that continue to provoke thought. His influence is everywhere, from the technology in our hands to the values we debate, from the classrooms of children to the laboratories probing the edge of space. In the end, Einstein's vision continues to shape the future because it was never only about physics. It was about seeing differently, thinking boldly, and uniting knowledge with humanity. His legacy is a reminder that the greatest discoveries are not only those that explain the cosmos, but those that illuminate what it means to be human. Einstein lives on not just in equations written on blackboards, but in the endless curiosity that drives each generation to ask, to seek, to imagine. As long as humanity looks to the stars and wonders about its place in the universe, Einstein's vision will remain alive, guiding, inspiring, and challenging us to go further.